Welcome, good morning, or everybody. If there's people time zones, good, whatever it is. I'm Phil, an application engineer at Maya, heat transfer in Montreal. Been with Maya for 18 years, and before that was in the industry for 10 years. And Mike, do you want to introduce Maya?
Yeah, Phil's a little modest. He says he's an application engineer at Maya. Phil's a principal at Maya, been around for a long time. He's not an application engineer. He's a software developer. He's a product manager. Him and Jacques are primarily responsible for SATK. They do a great job for us. For those of you that are on the line that don't know anything about Maya, we are Siemens PLM partner, our value-added reseller. We're also an integrated software developer. So we develop many of the tools that are available in the Siemens NX line of CAE products. A lot of them. We probably got about 60 modules that we develop for Siemens, the CAE front. So join the hip with Siemens. But what we're talking about to you guys about today is the Structural Analysis Toolkit for Nastran. And you guys went through an extensive evaluation on NX response versus SATK, and I think everybody's probably seen the numbers internally. And I'm pretty proud of this project. We hope you continue to realize the benefits of it. So we're here today to do probably almost a 4-hour training session, just an introduction to SATK. Earlier, there's some elements of SATK that you guys really don't even know about. You got full capabilities, you've got the basic module, you've got the advanced modules. You've pretty much been focusing on the random aspect of it, but I think Phil's going to try to cover today, at least introduce you to some of the other modules of SATK that may benefit you, that you don't even know that you got right now. So anyway, so let's start this off. We got probably the next 3.5, 3:45 to go this. And like I said, follow the training today. This is pretty much a download. It's a whole lot of interaction. There's not tutorials, but we only make available the temporary licenses to put on your SIL server that you guys can access if you want to run your own here in the near future. So, Phil.
And Jacques Dupos is with us. He's a developer of the product manager of SAT Toolkit, so it's really his baby. And I think he's done an outstanding job, and I guess the performance numbers you've shown is substantiate that. So my presentation, I have about 120 slides. I have 6 demos. You don't need a license. There are no tutorials this morning. As Mike said, there will be some additional licenses available on request. I'm able to try out the code yourself on your own problems. There are example problems. We'll discuss that later. So, any questions as we go along? Ask slow down because I tend to go too fast. And so this is what we're going to be covering.
I think everybody's as smart as you.
Oh, they're smarter than that. So the content of today's presentation is we're going to look at the SAT Toolkit main user interface, and then we're going to look at 4 of the tools. There's 8 tools in all that come with the product. We're going to what we call dynamic tools. So we're going to look at the random vibration processor. Performs a base excitation, a frequency domain for random vibration. And then from a solution 103 Nastran run. And we're going to look at the sine processor, which does a similar type of job, but with harmonic excitation. And tools that we use here in our own work services work, and we use the tool quite often. And so we will try to understand what the tool content is of our structures using the modal processor and the energy processor. There's 4 that come with the toolkit for the processors, and if you're interested, we can go over them at the end or when I'm done with the main presentation. Interested?
Interesting.
I'll just go do a brief overview, and I'll give you what's available to you. So, the Analysis Toolkit, how this came about to be was from a previous incarnation at Sparrow Space, which is now MDA. We found that Nastran was not, and Patran and whatever we were using at the time wasn't quite cutting it in terms of our needs. So we started doing our own code, and then we joined Mike. We redid the everything better, and code extensively here. So, and originally it was meant for to be integrated into FEMAP, and now it's a standalone tool. So, Mike mentioned that we are Siemens development partner. A lot of our products are have the Siemens name on them. Not this one. This is a Maya product. It's standalone. However, it's getting closer and closer to NX now. So, showing you how to create the input files in NX and post-processing the results, some of the results in NX. But it does not query an NX license, as was mentioned before. It queries the Maya license server, which you must download. So that's the product. So if you look at the main dialog, there's 5 buttons at the top. File. It allows you to open OP2 files. So you're not accessing solutions. We're accessing directly OP2 files. So when you open an OP2 file,
to be clear, what you've done is a lot of modal analysis, pretty much the same as you would have already done, and now you do the post-processing stresses, random vibration. Created an OP2 file, and he's opening it up now.
Yeah, well, there's other processors, of course, that don't use the modal results, but they basically all the processors use Nastran results to start off with, be they static or transient or in this case modal. So it would go and open the OP2 file that you want to process. We support MSC Nastran and NX Nastran OP2 files. You guys are using NX. And there's a variety of formats for OP2 files. We support the default formats that come out of NX. If you start with those, you may not be able to read the OP2 file into the toolkit. But I'll show you what the requirements are for toolkit to process the OP2 files in terms of Nastran syntax. By the way, are you familiar with what's your familiarity with NX Nastran? Is it beginner? Is it like if you had the syntax of the input file?
I'm moderate on my end for everybody.
Yeah, I was a beginner on my end. Yeah.
Okay. Well, I'll bring some of the cards. We call them cards, or some of the keywords that of the input file that SAT Toolkit's expecting. So you don't necessarily need to go into everything works out fine. Then you don't really care about that. But if you hit a snag, then it's good to understand what is written to the some of these keywords are and what the requirements are by SAT Toolkit. OP2 file. The main dialog here will parse the file, and it's gonna actually. Some of you guys should. I hear some background noise. Maybe it's best to go to mute yourself. So, what the toolkit does is dialog is it parses the OP2 file and it shows you the data blocks, the Nastran data blocks that are in it, and you can see some of them listed here. So that's been, and then what we found is that for some really large OP2 files, files. This took time, you know, a minute, maybe 2 minutes. So we did quick open. Doesn't scan the OP2 file. So we don't know if data blocks are available. It enables you all the dynamic processors. And if there's something missing in the OP2 file, then the error will be trapped by the processors themselves. Otherwise, data blocks, the program will be available to you, depending on what's in them. So that if you open, and then you go to tools, you'll see which processors can be used. If you use quick open, then you basically have to know what you're doing. There's a project you can set. So by default, the project defines the output file names, and by default it's the OP2 file name with a subscript which corresponds to the processor that you're using. But you control over that. You can name the project whatever you want. The next menu item is groups. So important because they allow you to generate margins of safety. In particular, or with the processor, or post-process just certain part of your model. You can create the groups yourself, group nodes or elements. Use dialogues that you see when you're output requests, or you can import them. As I mentioned before, we essentially started building this for FEMAP. So you'll see a lot of references for FEMAP, but in our case, what we want to do here from NX is import those groups from a universal file, and I'll show you how to create the groups, export the groups in universal file format. So you can if you want. This is how it's a bit convoluted. In the future, we certainly going to move on that, but when in NX you have these languages or these solvers that you pick when you create a FEM. So what you do is to change your solver. So in the Simpligator, select your FEM, you edit the FEM, and then you change your solver from NX Nastran to IDEA's UNV. And then you export simulation from the NX main menu bar. And what that will do is it's going to export the entire model into the universal file, including the groups that you've defined. And caveat here, well, first the groups must contain nodes and/or elements. So this is really what the toolkit's using. It's not using any entities. NX by default tries to put only meshes in the groups because it's simpler than putting all the elements in the mesh. It's lighter. But you got to make sure that you have the elements as well, not the mesh, but the elements. So I'll show you how to do that if you're not familiar with NX group functionality. Once you selected your OP2 file, and once you've imported your groups, you can see that they're available, as I mentioned before. If you open OP2 file, so only the tools that are that reference the information in the OP2 file are available. Yeah. Quick open, then only the dynamic tools are available. Those energy, random, modal, and sign. Menu here launches a dialog which is really informational. It shows you all the files you've created for the project. You can't edit them. You can't edit them. So this is something that concept of managing. We have pushed really to as far as we could have, but this is something that is not as useful as it could be right now. And finally, so it launches a table of contents for online help. So the full toolkit documentation. So we'll take a look. See the documentation.
Yep.
Okay. So you have prerequisites overall for working with the toolkit, and then you got a session for every processor. So let's look at what results are generated. No results, elemental results. Definition file, I'll be talking about that briefly, but this is a detailed description of the definition file. If you get advanced with SA Toolkit, you'll probably be wanting to manually edit this definition file because it's faster in some cases. So documentation, you clearly see what's generated by SA Toolkit in terms of results and in what format. And a bit of theoretical background, and how to prepare input file as well, your Nastran input file. So that's help table of contents. Then there's on context help. So whenever you're in the dialog, you just see a help. For example, go to you'll see help here, and then the context help will appear for that dialog. What's new? So Jacques actively maintains SA Toolkit, and you can see which what enhancements and bug fixes were introduced in each revision. So see what's been introduced in 602. And of course, we make sure we support the latest versions of NX and MSC Nastran. So we dock each one, and then we connect to SO 601, 6, and all. So gives you an idea. If you're not sure if your version supports this enhancement or that, you can refer to that page here. And here's where they need to rewrite because these examples are based on FEMAP. So as you're starting from FEMAP, and they're dated. So I rewrite them, or we will rewrite them and provide you with examples. I mean, they're step by step, so you can certainly go off and do them, but some are, it is my point to FEMAP, are not relevant for you guys. Troubleshooting, the typical we see. We can't open an OP2 file. Nothing happens when you open it. Typical thing: are you sure that your Nastran solution's finished? Make sure there's no fatal error in your Nastran solution. That's one of the common things. The common thing is, well, I can't get the results that I want in SA Toolkit. Well, it's a process. So you ask in your prior Nastran solution, your SOL 103, you have to ask for the results that you know you're going to want to process. So that's typical. We're gotten to ask for stresses, say, and then you want to, in SA Toolkit, you ask for stresses and nothing comes out. That's because they're not in the OP2 file. Macros, and you have to set the permissions in Excel to run macros. Except and the thing for you guys is knowing where the Nastran and the X help is. So there's documentation for NX10 is available. Of course, you can download it from GTAC. You can also reference it on the internet. You don't need to download it. And what's about the NX10? I believe this is the version you're using. NX10, is that correct?
Yeah, 185. Okay.
Those of you that are on 10, even if you're on 8.5, you can put to this. I can think this uses. It's built on Java again, which is a no. But what's nice about it is it doesn't run Java applets, so it's not always into little Java problems. Search is better than the previous versions. Advanced search really works when you put two exam vectors here. You will find the hits that you want. So this is N documentation, and if you dig a bit into NX, I have NX Nastran documentation here. And one thing that's really handy is the quick reference guide. So the quick guide's got a description of all the keywords of the cards, and some of which we'll be looking at today. So if you understand what they mean, this would be where you'd be going here. And there's a very small start button on the bottom right. So find your, once you've picked your OP2 file, you've imported your groups, you've clicked on tools, you've defined the contents of your processor, your options, then you click the start button. And then we actually launched the executable for the core code, the processor, and the bug tells picks the processor and wrote a definition file, and then tells the processor where to find the definition file. So it's kind of like NX. You know, when you're using NXCAE and you want to do an Nastran solve, well, NX is going to write an input file. Nastran to disk is going to launch the Nastran executable and tell Nastran where to find the Nastran input file. So this is a similar process here. You will get images you see here in the monitor are also stored to a log file. And if you run into a problem, it's good that you want to debug, help you debug the problem. Then you send an email to support@myhtt.com. Attach your log files, give us an idea of what the problem could be. What is SA Toolkit then? Well, it's many things. It's a no file reader, so we don't read NX solutions. We read two files directly, and that gives us latitude in terms of being performant and getting what we want. Part of what makes SA Toolkit performant reader is quick. You can use DMAP, or if you don't have a DMAP license and you use Nastran, you can point to delivery databases. You would do this in particular to use the residual flexibility method to account for modal truncation. Well, it's a use, and I've been showing you to the interface, and that's in setk.exe in the installation directory. Suitable is called sattools.exe, and the reason I specify in particular is that you can run sattools.exe alone. You don't need to start the executable. So you can sattools on any machine that's networked and that can query the license, and because we recognize the importance of you to be able to run in batch, so you can actually create batch files, and I'll be doing that for you today, where you have many jobs queued up one after the other. Of what to do to freeze your desktop and really to extract maximum performance, because these jobs can take time even if they're faster than our competitors. And then the SA Toolkit also, if you want, a report writer. We data that HTML pages. We populate Excel files, and we have macros that operate on the Excel files to give you a report-ready type of results. Okay. So definition files. As I mentioned before, the main is going to create a definition file. The termination is a .imp. It's going to write to disk. And the convention is the project _ the processor .imp. What you can do is you can manually edit these def files, or once you've created, you can reload them into the interface. If you're going to processor standalone, it means you've created one of these files and you're going to you're going to reference it. And I'll show you how to do that. So, let's get a definition file here. So I've done some SA Toolkit runs done already. Here. So this is a random OP2 file, sorry, MP file. You can see it's got the underscore random in name, so that's why we know what it is. So this syntax is all described in detail in the online help. To start manually editing it, you're going to find that you know, be very careful about how you do it. You can't introduce just any keyword anywhere. There's you know, there's something that the processor is assuming. So one of the three load cases, load case 1, this is for the random processor, so I'm loading an X. I've got my PSD defined here. Then I got a second load case, and it all comes from here. Number of load cases here being equal to 3. So it is expecting a second and a third, and the PSD definition for the second, PSD definition for the third. And the way the PSDs are written is frequency PSD, start, and then endpoint. PSD, 99, which ends. Here the PSD is broken into three rows here. So I can modify this. So for example, I could say, well, I'm just going to take that last row. I'm just going to put 2, and then I'm going to go directly to 2,000 hertz, and then we're going to change the level, 20 G squared per hertz. And I can just.
Where you don't have to change it here. I normally do it in the other dialog. I actually myself edited the input file.
And you can read the input file and then edit it in the dialog. I want to show you that you edited by hand. That's just the bottom line, and especially since you're able to run statutools.exe off the command line, and the ability to manually edit these files can be interesting for you. So, for example, you can remove a load case. You know, or again, if you only have one load case, you can add 1 or 2. Right. So well, let's do an open on this file here. This is my file that I've been processing here with this IMP file. So what we can do is in random analysis here, I can just go point to that definition file that I just edited right now. Go load. So now the changes that I've made here are, I can see UI. Yeah, I've changed my PSD here to 0.3. I go to 2,000 hertz. Yeah. Just go OK out of here, and then click Start, and my processor starts. Trick though is you don't have to load it into the IMP into the random analysis dialog here. Just edit this like this and add whatever I want here. I can add a third row, say. Go to 3/3, say. Right, and then I can just press. Okay, I don't load it. This is parsing that. Error parsing input file. So you got to be careful when you do that. I do wrong here. Oh, I forgot the 99. Okay. Now it's taking it. So this is what you have. And if you're going to be a high-end user, say, if you're going to use this this tool quite a bit, this might be interesting for you. And the rest of my presentation, I'll be showing you how to use the dogs in the user interface, just so you know you can do this. So I mentioned you can launch the SA Toolkit by clicking the Start button, as I've just done. You can start it from the command line, and next is as follows. So you point to the executable. You got 4 arguments. The first is the OP2 file name. This one is a definition file name. So seeing what the default syntax for the definition file is and how you can find a project and change it. Here's where you can define a new project name. This would be the third argument. And D is an integer code. Since the processors, we have 1 executable, so the integer actually points to the processor that you want to run. If you're going to do that, manually, you have to make in the tool in the shell, because you can do this on Linux as well. Here, I mean, the syntax I'm showing here is for Windows, as a Windows command tool, but this can be run off of the Linux shell. You need to do the license server, the location of the installation, and then to do this, right? So, give me a small example. I've made a batch file here, so I've already got. Would this be for you guys, running it off the command line?
Sure. All knowledge is good knowledge.
Okay. So this batch file. You can do this directly in the command as well. I'm just using this editor, and I'm just dumping the contents of my slide here. I need to so this is an environment variable I've just defined. Location. Hold on a sec. So yeah, so satools.exe is 1 level down here in the installation. So if you go to your SatTools installation, you go to 64. There's the core the processor executable right there, right? So things faster. I'm just gonna paste this line here. Path to my executable, my file name, my definition file name, a new name. I just put test, but I can, I don't know. February 29th. February 29th. And then code. This I'm running the modal summary, so it's code 8. Here's Bell. So this is the equivalent of what you see in the, this is a log file, basically. So I run the processor here, the motor processor. Is that clear? Good. What type of output files does SA Toolkit produce? Well, we talked about the log file. So the log file has run messages and warnings and error messages. There's some file. It's a summary file. It's really an echo of the settings. We rely. Whoops. whoops, we run on text output as well, so it's kind of boring. Most of the time, you want to send the data directly to NX, or but sometimes it's nice to have an output file to be able to parse. And the random processors will create HTML pages with pictures in PNG format with trees. So those could be quickly used for quick reports. We have an Excel. We create Excel files, and when we created the toolkit, we created for both Linux and Excel and Windows. So you create Excel files even if you're running on Linux. But because of the libraries we use, we can't get any files that are bigger than 7 megabytes, which is pretty limited. So to dump all your data to an Excel file, you probably want to dump group data or summary data. Once the file exceeds 7 megabytes, you can't do anything with it. We dump all the contents of the Excel file also to an XML file, which does not have any size limitations. So you can have a 2 gigabyte XML file if you want. Mostly though, for you guys is you write data to OP2 file for the processor. The OP2 format is binary. To universal files and universal files, and this is what NX is going to allow you to post-process for both your contour results, data, or for your XY plots, your charts. So if you want results as a function of frequency, for example, that for your power spectral density of acceleration or your stress component as a function of frequency, then you can use one of those formats. So as I mentioned at the beginning of my presentation, we call the dynamic tools. So the sine and random events that we support are base-driven. Okay, so the vertical application of base-driven vibration, which is prevalent in several industries, automotive, space, defense. And what's important when you're using that type of excitation is you got, and we're of course modal solutions. We're not using any direction. Please go on mute, please. I can hear some background noise. So what's important to understand your modal basis, because you'd be specifically exciting modes and perhaps not others. You understand, do your modes form a valid basis for in terms of effective mass? Do we have enough rigid body mass included in all the modes here, or do we have modal truncation effects? And that's to get effective mass as well. So the processor allows you to do that, and the energy processor helps you to understand what your structure participates in each mode. So if you're analyzing a single part, it's not a big deal, but if you're analyzing an assembly, and you understand which part of the assembly is responding, or which part of the assembly is being trained as a function of the response, then the energy processor can be very interesting. So let me ask you now, do you analyze single parts, or do you guys analyze assemblies typically?
Always.
Yeah. So in this case, you may be the energy processor may be quite interesting for you. So one of it is, and the energy, like all the other processors, it runs off of a Nastran solution. In this case, a solution 103, maybe the same type of the same OP2 actually that you would use for random. It allows you to post-process your modal strain kinetic energies for selected groups or for selected modes. And there's an output that's particularly useful. We use macros and we automatically generate the type of plot you see here. And your kinetic energies as a function of mode or group. So really, you'll have an understanding of your modes in your assembly. So the kinetic gives you a measure of which masses are excited the most mode. So it's by multiplying the elemental mass matrix by the velocity eigenvectors. Strand request. So now we'll generate these kinetic energies for each of the modes. Energies. So the strain energy helps you determine which part of your structure is experiencing maximum strain, and computed by multiplying elemental stiffness matrix by the displacement eigenvectors. Known as elastic potential energy or energy of deformation. And when you ask for strain energy, you'll also see Nastran will also compute strain energy density result. And right here it's dividing by the volume of the element. And if you're not interested in that as well. So about Nastran syntax before. So this the Nastran syntax looks for your solution 103 in the energy processor. So of course you want to call solution 103 normal modes solution. Then in the control, this is select your output requests and your you find labels for loads and boundary conditions. You want to pick strain energy and EK, kinetic energy. Find folds here. The reason you want to find a threshold for strain energy is that Nastran will not dump strain energies into the OP2 file for heritage reasons. You'll be missing some strain energy unless you define a very low threshold, say 0 or a very small number. You can param here. So in the bulk data, you can use this param comma tiny to define the threshold for strain energy. And the next Nastran solution, under the parameters tab, you can edit the solution parameters, and of course, under the case control tab, you can define your output request. Now, by the way, I will send you a PDF of this presentation. So this records, this might be interesting to have. What's optional here in terms of the setup for each processor is in blue here. So the param tiny is optional. Running Nastran solutions from NX Nastran from NX. Okay. So I'll be showing you then. I'll be showing you set that up for each processor. And Nastran does suppress strain energies by default, which are small. I mean, you want to really you want to add them here because imagine a global mode. Imagine a beam. Imagine that you're modeling a beam using solid elements for some reason, and you've got many solid elements to model that beam. Well, kinetic energies are all going to be pretty small for each element, but yet to get they find the first mode of that beam. And, you need to capture energies in your OP2 file to really understand the modes. So the processor dialog looks like this. And each dialog is similar, actually. At the top of the dialog, you can set a definition file and load it. So if you create in the past and you want to use the group definitions or whatever else you've defined, then you can just load it. And you can strain energies or kinetic energies at both. And by default, you use all the elements. But what's more interesting, I think, is if you split up your model into groups and have the processor tabulate the strain and kinetic energies by group, even if the groups comprise the totality of your model. And then you can pick the natural frequencies that that you want to include in your processor. Either by default it's all, or you can click mode frequency ranges if you don't want all the modes. Of course, by function we write data out to a text file or ASCII file, and you'll use Excel here. So I don't know why it's not on by default, but you click Excel here and data will go there. You know, by default, the data written to Excel and then text file are for the groups only that you pick, but you can also have the listing of all the elements if you select elements as well, but then your file will get much bigger. So this and this would be a text file output. So you have by mode. You would see the ID, the frequency, the name of the group, and this is an example. We've picked a variety of groups here. And see the percent strain energy for each group. Then the total energy, right, which depends on elements in your group. If you don't have all the elements, then your total may not be 100. Total is the total energy for all the elements in the model, regardless of the groups you've defined, and should be 100%. Won't be if your thresholds haven't been defined. So forth by mode. This in Excel format where we have a matrix where the columns are the modes, and then the groups signed by rows. And then is available. So we have a macro that's available when you've used the group option. You to sort by group or by mode in the Excel file, and I'll be showing you how that works. It's a nice 3D graph here. Energy by mode by group number, or group name rather. Which may report. So what's the processor here? Any questions, processor? Before will I set it up? All right. So what I is a model of a space antenna actually. So it's a composite structure, like feed here in the middle. It's metallic composite, and it's kind of using rigid elements or coincident nodes. So it's relatively small for the purposes of my demo here. Fem and an Nastran sim, and I'm going to do is create a new solution. Solution values. I'll be a new solution for each of these processes. I want you to know you can create the same OP2 file and use them in all processors. There's difference between them, but I don't want to show you what they are. So for create, I'm going to create this parent tiny I told you about. So I'm going to click on create all objects. And the supports all the params that Nastran, NX Nastran version of which supports. So if I go to S to T, on something small, I could put 0, I suppose. Turn it. Edit. I'm going to create a new modeling object for the output request. And strain energy. And here's what can be defined here for strain energy. stresses are generated. I don't need them. I can turn that off. I think that's pretty much it. By default, the first tested and that is. I'm just constraint here. So I had a single constraint at the base of my structure. This is important. If you're doing excitation, you're really exciting a single node and connecting that node rigidly to the interface points on your structure. So that node comes, I mean, in this case, just a straight processor, but for the random in the side, these become the shaker essentially. If you know, this is what's moving up and down or left and right. So I'm just turn off solve.
So I have a question. Necessarily to do with the SI toolkit, but you know, you just said you want to have a single node.
Yep.
So that's fine. But let's say you want to extract 1 sigma, if it's a random analysis, reaction forces at the mounting points rather than just a single node. If I understand it correctly, it's kind of difficult to get that at those mounting points. So
not used. I mean, what you can do here is you can put I mean, you can have beam elements if you want. What we typically use is we'll put spring elements is what we typically do between the rigid element and the structure where there's an interface bolt here, and we'll see from the random processor extract the forces for those springs. So those could be beam elements, or it could be MPC forces. So if you ask for MPC force output, you will get force at these nodes here, and you could use those.
okay, thanks.
I'm getting my first 10 modes are between 30 hertz and 59 hertz. And even though you can see displacement and the strain energy and the kinetic energy can be processed by an X. Mention is density results as well. Come out. But this means we have an OP2 file that's written to disk, and so we're going to go process it. So I'm going to do an open. My OP file. Kinetic energy, strain energy. A reaction force. And I'm going to export these groups from this model. So if I go to FEM, 5 groups here. Return to my model. Groups for some of the panels here. Subreflector. And you want to right click and you go information. And let me get my information window here. So you can see I have 94 elements, I have 15 nodes, and I have 1 mesh. The reason I was thinking about meshes before is let's look at this group here. I did it on purpose. This feed group here, if I do information on it, I have 4 nodes that I put manually, and I have 1 mesh. So if you go, automatic group, for example, and you go, which is what I did, and you create groups with the same physical property, it's going to dump meshes in here. So you want to be able to export to universal file format, you need to have elements. So what you need to go add to group, you see this as element, pick these elements. It says I have 304, I go OK. And then when I pick the group and I go information, I hash, but I have the discrete elements. So this is what you need. Is I'm going to universal file so I can reuse by the processor. I'm going to change this. I'm going to edit my FEM and I can change to any solver. I'm going to pick ID as UNV here, the universal file format that we're seeking. So now to universal language and export it. I'm going to go File, Export, Simulation. That I want, and then define an output file. Okay. Giving me messages for just about everything. You know, notes, physical properties, elements, and then it's type groups exported. Zero group skipped. So that's what I want to see here. If you only have a group with a mesh in it, it's going to say one group skip, for example, or two, etc. Good. I'm back to NX Nastran FM and do in Toolkit main dialog. I could go groups, import from universal file, and this is the file I just exported here. So it does, but you'll be able to see the groups later in the tools. So I go to tools. On the data I have energy analysis that's available to me. And what we're going to pick all the groups that we've read in. So groups that have elements in them. Switch them from the inactive window to the active window. Like reflector, main reflector, feed. And I'll do the same for kinetic energy. And you can, this is something you can do. You can just give it whatever name you want. You can edit labels, so it's 100,000. Put the ranges as well using these brackets. So I can go from 1 to 200. I can create them, but I don't. In this case, I'm not going to use it. I'm going to process all the modes, and I'm going to dump my data to Excel. Things. So I click dialog, and then that writes a definition file. And when I click Start, the tool processes that definition file with the right processor. So to run, I got no warnings, no errors. So if I go I got an output file here. It's an ASCII file. Before you get the bind the kinetic energy results for each group. More interesting file. So I'll open the kinetic energy file. And it's in my other screen here. Hold on. Macro. You can change my here to whatever you want. Template file. Look at the here. So what are my modes? What these are my groups. I'm tiny. My are 100%. So meaning, and my groups don't overlap. So meaning that the total energy in each group, if I add them all up, I get 100% of the strain energy in the model, which is the total here. What additional formatting say? So for the reflector, 1 and mode 4 are the ones with lots of kinetic energy or lots of displacement. For the side panels, it's modes 2 and 3, 5, 6, 8, 9, 10. For the subreflector, it's modes 7 and 8. What I can do is and then I can sort these by a group, say. So I can say, let's look at there's nothing much for the feed. Let's say the main reflector. So it did the groups by descending strain energy. So group 4 has got the most strain energy for this group, and then 1 is got 64%. Can pick another group, and then have descending strain energy. I can put this, and then I can sort by mode. So like mode 1, let's look at by descending strain energy, which group is more important. So the main reflector has got most strain energy, then the side panels and the feed. It's complex. This can be really invaluable because it's telling you where stuff is happening. I mean, it might be obvious when you look at an animation which part of the structure is straining. Certainly, you might get a feel for what's displacing. Connect for the strain, it might not be that obvious. That's generated for you. So we have a 3D chart, and if I click here, 3D rotation. And this is ability here. And once I have a macro, I could just save it. So the next time I open it. File energy. For kinetic energy. Open. For kinetic energy here. Of course, that's completely different because here we're looking at the displacement rather than strain, or velocity rather than strain. Is this something that for you guys?
At least I can.
Right. Again, this data is in an X, but to get it, you'd have to format it quite a bit to be able to size it in the way we've shown it to you. So the next, talk about the modal processor or the modal summary. Understand which modes of high effective mass and high response actually as well. So there's two: is modal effective masses or weights, and action. So the percentage of modal weight compared to the rigid body weight in each direction. Gives you of which are the key modes. So if you have lots of mass participating in a mode, then you have lots of stress when you excite it. Also look at prediction. What we do is we create a G-harmonic excitation at the base, and we allow you to pick nodes and degrees of freedom at which you want to see responses. So to identify local modes, may have small effective mass, but still have high responses. So with lots of mass, and then also modes with lots of response, and together it gives you a pretty robust picture where your problems could be on your structure, which modes are important for you. And so weight is the square essentially of the modal participation factor. And fraction is your modal effective weight divided by the total components of the mass matrix here, which Nastran outputs to the grid point weight generator. That output, the grid point weight generator, in my next demo. And factors is the generalized mass matrix, the displacement vectors, the reduced mass matrix, and the rigid body modes. And talking mass and weight, but we use weight here because this is weight mass that you can put in here. So there's a parameter in Nastran called weight mass. It's essentially mass to weight if you want. And you can use it to help. It really scales the mass matrix, but in the preprocessor allows you to define your units mass and all mass-related properties as weight. So, for example, you can define as pound masses rather than pound seconds squared per inch. This great weight generator shows you the weight, not mass. So if you got a weight mass, it's accounted for in this table. What unit working typically?
For me, back and forth, depending.
Yeah. Well, if you define NX, it will allow you to define your masses, and if you're using imperial units, you know, because allow you to define your masses and pound masses, and does all this for you. But if ever you run into a model with weight mass parameter in it, which does the same thing, then this gives you a bit of the background as to why it exists and where it's used. And this is a tabular or ASCII format. Will give you a list of your eigenvalues, your modes, frequency, your mass by coordinate system, x, y, z, sorry, and then your fractions. Also add the rotational degrees of freedom. Mass in each direction. And then your cumulative effective mass. And this is important because when you're using base excitation, modal basis should include all your, when you look at mass, your total mass fraction, it should be as close to 100% of your rigid body mass as possible in each direction. And how far from that 100% tells you have to use, you have to compensate for modal truncation. So modal truncation is you're missing rigid body mass really in your modal basis is what it is, and we'll be discussing that later. So that was for effective. And going here, you can Nastran writes this out to the FO6 file. You can edit the FO6 file of Nastran and just copy and paste it into a spreadsheet if you want. I personally don't really care for copying and pasting on a recurring basis, so I much prefer to use this form in this tool. So what the processor also does, as I mentioned before, is it calculates a response to a steady state excitation of 1G in freedom you specify. So what is it? Well, if you look at your equation of motion here, you express it in the modal basis. So you express displacement by a function of the eigenvector as modal. And that is your Q as a function of harmonic excitation, so format A, e to j omega t, to get state harmonic response. Then response that we calculate in total summary, and also in the sign processor, which is the next section that we're going to look at. Right, is your acceleration plus your dynamic response, which is omega squared times the sum of the transfer function h times the eigenvector times your modal participation factor. And this transfer function h is 1, this is classic here, you must have seen this before, is 1 divided by omega squared. So omega p here is your fundamental frequency, omega is your excitation frequency, and then plus j omega p divided by q for the amplification factor. You are to your natural frequency, the more response you get, and the more amplification you have, the higher it's going to be, your response that is, and you're probably off. So how to set up a processor in the Nastran deck? So using Nastran syntax, again using a solution 103 normal modes analysis, iterative control. In the case, you must request displacements, and it's optional, but if you're going to post-process responses, you've got to put displacement for at least a set of your model or all. Strain your model. Request modal effective mass from Nastran, and you must send it to the OP2 file, so it ought to be here with the option plot. Option here is not necessary. You can specify a grid around which the rotational are accounted for. In the you need parent post -2, and that's the NX default. So NX, I'll change it. It's always going to write parent post -2. It's always going to write parent post DXTS. So I'm just put information. That's what NX outputs by default. Now, if your mass or weight fractions, you're going to need to put this here. GRTNT, comma x is either a node, or it's, if you put 0, it's the origin of the global coordinate system. Calculator. And that's optional, but if you want fractions, I think it's handier to put it in. Then your SBC card, so your nodal constraint. At the modal processor dialog, at the top, as for every processor, we have the name and path to the definition file. Two sections: a section for effective masses and a section for response prediction. Choice with just translational masses or all, of course, where you have rotational effective masses, which would be, imagine a cantilever beam. Then you get a high rotational effective mass for the axis that's out of the paper, out of the screen. Then so a percent, which is a percent of the rigid mass. So any mode with any component that has more than this percent effective mass will get highlighted. Will get. For response, you can select groups, and the results will be shown by group. Pick an evaluation method as being either exact or approximate. If you use the exact method, we use all the modes in your solution 103 to calculate the response. If it's approximate, we only use the mode that corresponds to the excitation frequency. And a data filter. So the data filter filters out small responses. So if you don't see responses less than so many G's, toggle that. The mode, it means that I want to see modes that have more than so many G's response for the node that I've selected. XI result combinations of amplification factor and your Excel file toggle, which truly should always be be on, and I believe it is in this dialog. We're going to see for the response predictions are like this. You're going to see case ID, and then you're going to see so lowercase case GX 1G. Then you get the response for the nodes you selected by frequency. You're going to see the X result, X magnitude, the Y magnitude, the Z magnitude, and then the root sum squared magnitude of all the components. And then that means that the magnitude here, one of the components has exceeded the filter you've defined. So it was 15 Gs. Well, here I have 18.8 Gs. And so this is what's considered to be a critical mode here. This mode here, 34.98. Okay. Then you get the effective mass result. Sorry. Then you have by mode, frequency. The mass is here in fractions, and the responses, the maximum response, which load the maximum response, which node it occurred at, which group, and then these stars here, essentially the asterisks, show which are the important modes. Either modes that have lots of effective mass, like 33%, response 38 Gs. This second mode here has got 6% effective mass in X, and it's got a 43 G maximum response at this node. So you get an idea of which modes have a lot of mass participation and have high responses. Modes may not have either, and you can, if you want, you can discard them from your analysis, or at least you worry less about them when you post-process. While we generate for you, we will create graphs on for you, and the graphs we create are effective mass by degree of freedom by mode, cumulative effective mass by degree of freedom by mode. We have formatted tables, so instead of having asterisks, we highlight the row for the modes that meet the criteria, the mode filters for and for responses. So why don't we a demo on how to use that tool? So I could edit this solution that I've created and just modify it a bit. I'm just going to again want to real value and PNT parameter here. Which is the basic coordinate system. And I'm going to put, well, displacement equals all. Let's see, what else do I need? I can always do this. I need this here, yeah? So if I go output request, model effective, I'm going to check that one, and I'm going to make sure the medium is set to plot. That's important, and it doesn't work. Request that works the other way than all the others. Disable stress, I don't really need it. And then I have to make my constraint. My constraint container and go add to active solution or step. I'm in a solution. I'm using NX 10.2, and I'm using NX 10.03. but all this will show in earlier versions. Make sure my results. Yeah, again, the same. Now what I'm going to do, I'm going to MP2 file, I've just generated here, and you can see dash. So, you know, it's not gave my solution a name, so it's, I'm using this with this just to use it for. And I'm going to go to modal. I want to see all masses that have translational mass components greater than 10% of the rigid mass. And for my I'm pick groups. I'm going to click nodes and feed here. I'm going to solve them. I want all the modes that have more than, say, 25 Gs of response for 1 G excitation. I don't want to see any modes, any responses below 10 Gs, and I'm going to load in the X. But I can also file. With the log settings, they've been written to a definition file, and now I just start. Actually, the definition file is being written now. I just start. That's good. Click OK, the definition file is being written then. So when you log. So straight to the Excel results. And again, we have it on this sheet. So in tab, you have an echo of your settings. Then a chart for effective mass. X, Y, and the Z affections. So the X fraction is in red. You can see mode is important and in what direction. So the Y mode is mode 6. Isn't much happening in Z. Cumulative mass, you can see it's really for the X direction, almost 7% after 10 modes. Then we have the so we see effective mass by translational degree, and then the fractions follow the next 3 columns. You can see here the order effective mass on by mode and back to this. So I had a bunch of nodes in this feed group, and I want to see all the modes that give me more than 25 G response. And the other that is mode at 47 Hertz. X of 35 G's magnitude, because you know these are complex results. The magnitude is 35 G's, and the 7 and the Z it's very small. So our magnitude displacement or acceleration is about 36 G's. In X and for loading in the Z, I had about 10 G's only. If I look at our right now. So it combines the modal effective mass and the responses that are interesting for me. And it shows which modes are important. So which modes have either more effective mass in any direction or have more 5G response in my group PPT feed. I could have put 10 groups here and the group name would be here. In one view here, all the modes have put a lot of stress because of effective mass, or stress because high response. This I think this looks pretty good in a report. You can just copy and paste that. Any Is that something for you guys?
Yes, but again, speak for everybody. Go ahead.
Yeah, it's a pretty way of doing it. I mean, I've normally been doing this from the FO6 file, just grabbing it from there, but this is more complete and gives more information.
Yeah, it's personal. Some people like copying and pasting. It just after a while it bugs me. So, you know, I just let the software do it. All right. So 2 processors that you can use that you have, and that can help you understand your mode, like what's included. Next, and use the really great animation tools to visualize each mode or the important modes. But 2 processors, then you have animations. I think you have a pretty full understanding of what's happening in your assembly. So now your base excitation. So I'm not in a processor at first. I know I've been using the random. There's an overlap between both, so it's not going to be. It will be pertinent for you. I don't know if you ever used this processor. Dave, yeah? Okay, so you have requirements then to perform harmonic base excitation analysis. This could be very important for you then.
Yes.
So what this processor does is steady state harmonization. We connect the transient, the response, look at state. So it's a deterministic periodic signal, input and response. If it's non, I mean, if it's the other end here, you could be doing transient analysis. So in a sine, you do a sine test, you do a analysis. So what this does is it similar to what an X-response sim does. It bases itself off of a Nastran normal mode solution. Vectors and grabs the rigid body modes and then it's the responses of your model for a harmonic base acceleration. Equivalent of response acceleration and also or Nastran solution 111, except it's a lot to use and it's faster. So the design and the random processors, they share the same Nastran solution sequence, share the same Nastran cards, and more or less the same restrictions in terms of which cards you can use. Features of the processor are the ability to include up to 10 subcases in a run, where a subcase is a combination of direction and input spectrum. Optional counts for modal truncation. So we looked at you know, the sum of the cumulative effective mass. So if it's not as high as you'd like it to be, say 90–95% of your rigid mass, then you probably want to turn this on, and you have that you can use to account truncation. So either residual vectors, which is the default method, or residual flexibility, which does the thing but differently using a DMAP. So DMAP is high-level Nastran language. I don't know if you guys are familiar with it. I don't know if you have a license for it. It is an option. Keep license.
I don't know if anybody else uses it.
Okay. Map, you need a license. However, we have a workaround such that you can use the capability without needing a license. So I'm going to discuss that briefly. Addition can be done using all loads at Nastran's computer, or you can select which ones you want to use. And it computes the absolute or the relative displacements, velocities, and acceleration. So relative would be interesting because, you know, if you're, I don't know if you guys go see the when they actually test this. Sign testing or random testing, typically done on a shaker. The shaker itself moves. So using a relative results remove that displacement of the input node shaker, which is important in, for those metrics. So we have the maxima overall frequencies. So my maximum response overall frequencies, it'll sit by frequency or by result, which would be no elemental, which in Nastran world is known as sort 1 and sort 2 options. If you look at your control output request, that's how they describe them. One features of the sign processor is that your results are complex, yeah. So you get calls for everything. What's for velocity stress? We figure out the phase at which the stress is maximum using analytical approach, which is very fast. And so we'll get maximum real von Mises stress, and we will compute margins of safety based on the von Mises stress automatically. And once we generate XY plots, which you can HTML pages in Excel or in the NX function navigator. Are you guys familiar with the NX function navigator? Okay, I guess I'll be giving you a little introduction to that today. So, vector approach for model truncation, we call it the MF-MAS approach. And all you need to enable this is to have this effective mass request in your case control. I've shown 4 for the modal summary. Same deal here for the sign and the random processors. You need, of course, a constraint as a single node. We've talked about that. And you need all your requests. So if you request displacement, velocity, or acceleration from the toolkit, you need this for displacements in the Nastran Sol 103 solution. If you're getting stresses from the toolkit, to ask for stresses in the Sol 103 solution. Similarly, for any other output request like force, MPC force, etc. That's is forgetting to add them, request them here. And in the bulk data, for information, I put the post -2 and post DXTS, as well as the SPC card. I'm going to use the residual vector approach, which is the MF-MAS approach. You need to add param res binary S, which you can add using the modeling objects as I've shown before, and we're going to do it here in my demo. If you're using an approach, it's a bit different. You don't need the MF-MAS card, but you need to point to the DMAP, use a statement, or if you don't have a DMAP license, then you point to a delivery database. If you go in the SA Toolkit help, and you sign, it doesn't matter, but say DMAP. It tells you what you need, what extra cards you need, what params you need, how to put DMAP or to a delivery database. A delivery database is essentially a solution sequence that includes a DMAP already for you, so you don't need to invoke the DMAP. a PDF of this, so you'll have reference.
Does the OEOM need to be
I'm
Does the OEOM parameter need to be set to global like it does in random for displacement?
Yeah, I didn't add it, but no, it doesn't actually. It doesn't because we're not writing the same data block as in random. But that's a question. This is parameter UG core global. So if I step ahead a couple of slides here and I go to the random processor. I'll get there eventually. I had. Okay, forget that. Then UG core, you need to set to toggle on. Where is it? You ask for acceleration, displacement, or velocity, and then you need to do that. Here. The reason is because, as I put notes here, the OP2 file doesn't have a data block. That's in the basic coordinate system. For the result, but only if we're not dumping data to the OP2 file in the SLIME processor, so that's why it's not required. Long story. Nope, don't need it. All right, truncation. Okay, this is from the NX Nastran Basic Dynamic Analysis Use Guide. So, we're accessing the NX and the NX Nastran online help. That guide can be found there. So possible, actually, it will happen that not all modes are computed, and it's certainly possible that you compute too many modes, but it's not generally the case. But Nastran recommends that you should include all the modes whose frequencies lie within the range of the forcing frequencies as a minimum. And if you're assigned to 100 Hertz, then you should at least compute all the modes to 100 Hertz. Absolute minimum. And for better accuracy, this guide recommends that you compute modes up to at least 2 or 3 times the highest forcing frequency. So you're going to go to 100 Hertz, then you should, if you're to 100 Hertz, then you should compute all the modes to 300, which is overkill, but that's really covering all the covering basics. Vectors can also be requested to improve the response by adding the missing static flexibility associated with the higher modes. Vector approach, then, again, from the same basic analysis dynamic analysis uses guide. So typically, the only subset of all the modes for the structure. I mean, it makes sense for performance reasons. So all the computed modes may represent most of the dynamic content of the structure. The omission of higher frequency modes can lead to errors, resulting response prediction. Higher frequencies do contribute statically to the response. And to palette problem is to use residual vectors. Right? Those vectors do contain that missing static map. So again, the first one is the residual vector approach that I've just talked about here, or what we call the MF-MAS approach. And here we're calculating extra eigenvectors. Right. And from this reference here, looking at the total forces and what we're doing is we're removing from the total forces. So the forces you get by moving between model. This is P, and you subtract the forces, the total forces, and you subtract the component of the forces from the loads that kept the solution. Okay. Then, using the inverse of the stiffness matrix, transforming these forces to displacements, so that these are obtained, and again, this is the contribution, and this is the contribution from the modes you've retained. Those vectors are orthogonal with respect to the mass and stiffness matrices. They're to the existing mode shapes. So they're your actual modes you request, the ones you're used to getting, to be your residual modes. And then mass and stiffness matrices are updated using all these modes, the total modal basis here, and represent the static response that's orthogonal to the retained modes, and they can be in the vectors that you're using for superposition. The DMAP approach, or residual flexibility, is similar. So you'll see that the equations come out to be very similar. If you assume that the excitation frequency is much lower than the frequency of the highest retained mode, where R means retained, okay, response is the total response is the dynamic response plus the static contribution, the static contribution of the missing modes, which is the static contribution using the stiffness matrix times the force due to enforced acceleration minus the contribution from the retained modes. Similar to in the second to last slide. The main difference is that this static contribution is added to the responses directly. There aren't extra modes you have to manage, which is nice. So you don't have to excite those modes; they don't exist. They're included already in the response. In an X response sim, you have a similar concept called the modal acceleration method, which does similar, which sums up the static contribution of the retained modes and then subtracts it from the total static contribution. So how does modal truncation show up in your results? I mean, for some science analysis, you'll see the difference really being between the natural frequencies. So, natural frequencies, you get such a huge imaginary response that really the dynamic imaginary response is basically everything. Between modes, you to see some difference. And what this plot shows is the result of 4 analyses. 2 analyses, so solution 111, which is modal, and solution 108, which is direct. Direct solution doesn't work in the modal basis and doesn't, so it's not subject to modal truncation, and that's really the exact response with the X's here. So you can see that off resonance, we're under-predicting the response with solution 111 with now a tool analysis without residual flexibility. We tend to follow each one of these solutions. So with the residual flexibility, this dashed line follows the Nastran solution 108 pretty clearly. Benefit of a direct analysis in the modal domain with extra residual flexibility components. The less cumulative effective mass you have, more this is important. If you're going to, you do a sign analysis and you excite off resonance, you say, well, I want to know what my response is at 20 Hertz, and the response is not equal to mass times your acceleration. You know why, right? You're really effective mass here. That make sense? So the sign is neatly organized. Again, processors. You're able to load existing definition file. Then you create cases. You see that you want to include in your full superposition. And you the damping, output preferences, and then for calculation and margin of safety calculation, here. Okay, definition. Load cases or subcases. Each sub points to a different output request. Okay? So I give it a flexibility. By default, it's a coordinate system, but you can pick another coordinate system. The axis citation, and you define input iteration. So iteration. Factor applies to the acceleration here. So, in consistent units, we'll talk about those later. Per second squared. But the function in G's here. And 386 on it, right? So, factor between G's and inch per second squared. Right, so you can work units at this point. Structural analysis toolkit is unitless. Okay, that's trying to care what units it's using for units, and there's information messages at the top, but that's really just for the post processor. Nastran doesn't give a hoot what you're using. So I have consistent units. I've extracted this table from PMAP1 training. You can see it on that, this type of table. Shows you what consistent units are. To define your input acceleration, you find it in consistent units. So that's, and using inches then, you've got to be inch per second squared. If you're using millimeters per second squared. You can Nastran solution, but the Nastran solution are those of your sim. Pound inch or millimeter is a million units. You know, you can select any unit system for your Nastran solution. So if I go to my is it here? Is slowing down the my applications here. Huh. Big time. Not bad. All right. No idea what happened. Next here. Continue. So solution, you can export basically your IMP file in any unit system you pick. Now the files from the SA toolkit includes files, WNX as companion results, and that in the solution units, and you're all set. I don't know if you're familiar. All right. You have a solution. You can add companion results, which are essentially results from a can be generated from a SAT. Essentially lumped in. They're essentially lumped into the main solution results. So when you attach those, make sure you're attaching them to the same solution that you've used to write your Sol 103. All right. Going back to our output requests. Output requests need a frequency set, which is an equivalent of Nastran bulk data FREC cards. FREC 1, FREC 2, FREC 3. Which excitation frequencies are considered? If you're going to create plots, you're more frequencies to have a nice smooth curve, yeah? But looking at your maximum result, you'll probably focus on the natural frequencies. So notice data and plot. So data is for tabular output, or creating contours in an NX. Was plot just HTML pages or plots in the NX function navigator. Von Mises safety for NX. The neutral toggle is on, so neutral actually, sorry, but it's not clear, but it generates a universal file. Options otherwise are very similar to the random processor. All your stresses, for example, here you can select groups, and then you click the yellow arrow here, and that gives you results. What's nice is you can ask for a result more than once, which you can't do in Nastran. So you can say, you can ask for accelerations to be sent text file, and then you can ask for another request for accelerations and send plots, say, to Excel with a different frequency set. The idea is to do a shot if you can. When you add accelerations, there's a scale factor that appears. The idea is to be able to post-process results in Gs rather than inch per second or millimeters per second squared. Be able to bring this back into an X. You define here. So in plots, contours, consistent units. So even if you find a scale factor here, we're still showing inch per second squared or millimeters per second squared. And issue in the NX function plots, the units that are shown are actually incorrect. And both of these issues will be fixed in the next release. Up, and you can have this slide for reference. Now, define a frequency set. A frequency set is where you want to excite, what frequencies you want to excite your structure. You can, so you're in your lower frequency, as well as natural frequencies, as well as intermediate frequencies between the bounds and the natural frequencies using FREC 2 or FREC 3 formats. FREC 2 are split up domain in however ranges, whereas FREC 3 will split up the frequencies between each mode shape. And then you get additional frequencies. So if you've got a breakpoint in your curve and a frequency, you can add it here, so your plots will actually show that breakpoint. So pretty thorough frequencies. So that's finding your frequency set for and your outputs. The model basis, you could pick modes, or mode ranges or frequency ranges. If you do a flexibility approach or the DMAP approach, you can check this on or off for the wrist flexibility effects. And then you have a toggle for absolute or relative piston velocity and acceleration. Is modal damping specified as an amplification factor Q, which is equal to the inverse of structural damping, which is equal to 1 over 2 zeta, where zeta is your critical damping ratio, or your damping. Modal is the only type of damping that the toolkit so define damping in the model, in the material words or in your spring elements. We will ignore that. Interpolate linear between each frequency. But, here we have complex results. So how do you want them? You want real imaginary? You want magnitude phase or magnitude only? For the text output mainly, and some of the plots. Details. High and low. You want group for the groups, or do you want complete data, including any groups you've defined and all the contents of the group? So lots of data. You want sort 1 or sort 2 format, so by frequency or by node and element. Here's a compute phase-consistent von Mises stresses using a numerical expression. It's not a numerical method, hence it's performant. So you need to get the von stresses and the margins of safety. You can't, if you just ask for stresses in the output request, it won't calculate the phase-consistent von Mises stress. So combination of elements, either all or selected groups, a double strength, safety factor. We use this equation here to generate margins of safety. And the stresses is that you this story in the OP2 file in the middle for that you define in an X. So unfortunately, even though you get group out of an X, you have to basically define your allowable stress, either yield or ultimate. That is just for information. And his story with this for the sign processor is the same as in the random processor. We will put von Mises stresses and associated margins for things that are less than the off here by 100%. Some people see everything. They want to see their margins all over the place, so just make that big. Make that, a million or 10 million. That's a legacy thing. In the past, it was hard to read a lot of data. And the processor is tough time processing it. Not the case anymore. Your von Mises stresses and your margins of safety only for margins that are lower than this cutoff. Here. The sign price, these pages, with the only come out in magnitude format, by the way, regardless of whether you picked real imaginary. But for these plots, they're only magnitude. You can get it all, and that's really nice. Same plots as an HTML page, but you can do stuff with this Excel data. For example, if you've got notching to add, your notching logic and see what it's going to give, then you can actually feed that back into the SA toolkit as a notched input. You can bring NX because the function tools are pretty good in actually they're excellent in NX. So we call the new associated function file an AFU file, and you import the universal file that SA Toolkit generated for you. Of next output for the von Mises stresses and margin of safety. Again, I rate, you need to click the button and generate stress cases to get that output. In here, current version of the sign processor only supports element centroid results. If you have this on your elements, only centroidal stresses are processed. That will be fixed in the next version, V7. So results in NX. It's time. So, on the sign processor, by the way. All right. Let me just next. I don't know why it bailed on me. I wasn't doing to it. This is going to take a 10-minute break and finish up with the random processor. So, residual flexibility or residual vectors, that's something that you guys would want to use.
Yeah, I don't think so. Not for me, but I don't know. Everybody else ever?
I'm wondering if we're having net issues here. Oh, it's really slow. Okay. Okay, well this up, I'm going to switch to my laptop.
It seems like the residual vectors, when I use them in other, in like Hatran or whatever, any other nest, it didn't seem to make that much difference in the result. So you showed it only at the low amplitude where it seemed to make a difference. So maybe that's why I never saw a big difference in like the result, because the peaks were the same. And you'd have to know, I guess, a lot like that, like you showed before.
Yeah, for some, for sure, that's the case. And it's
I mean, the overall RMS value wasn't like noticeably different. So right, being by the peaks, and the peaks were the same.
Well, the S is not just driven by the peaks; it's also driven by the valleys. So if you're wrong,
well,
you're gonna yeah, mainly the peaks. It really affects the RMS in random, and so if you have serious truncation, you might notice it. Okay, here with NX. Let me try it again. Let me check my mails. Yikes. I use 350 days a year, and
So far, I normally do veneer for residual effects, but I can't say I've studied it. I just hit the button. Yeah.
Got two on. Okay. And
Well, there's some things, probably when you're doing like a sharp response, you're not supposed to use it. I give you an answer.
yeah.
Like SRS or for a sign.
Yeah. No. I think when you're doing SRS.
Analysis reasons. I don't know.
I think they told us that in one of our training things. And then I've used it and I noticed, the results were way too high.
Yeah.
So, I'll use a version of NX10. I think our network is crapped out. Actually, if this doesn't start soon, we'll take a break now. Man, it's dreadful. All right, we should take a break. Let's take a 10-minute break. So back at WEST. Okay, some minutes from now. A washroom break or a coffee break, whatever, and I'll try to get an export here.
10.
All right. I'll resume in 15 minutes. Join me. Can I do that? Hello, you there?
Here.
Able to stop. So I'm for some reason X isn't working here on my desktop. So no problem.
Okay.
Continue. So 10 I'll continue unless you want me to wait a bit more.
Yes, we can continue.
All right. So was this useful what I've been presenting? Is there, am I too much detail? Is it comment, anything?
Appreciate it. I tend to want to concentrate on the buttons to push for the push that button. The theory behind it is good. Also, it's a need to know, or at least it's there.
Well, you get some button pushing soon. And this you can see on my screen there. Does it show? No, you don't see it. All right, but so what I'll do is the sign processor, and then that works. Again, I'll create a 1-3 real eigenvalue solution. I'll go to case control, define my output request. So we want math.
I've been doing real eigenvalues, but there are other options also, right? That does it matter that much or not?
If you respond sim, it might work. For you. Might work for you. I can't remember it by heart. Hold on.
The response sim works.
Response sim will work, but the response sim DMAP or embedded DMAP will extract eigenvectors, constraint modes, attachment modes that in your binary file, and so you're going to get a bigger OP2 file than you really need, and the response sim DMAP might have some limitations or restrictions that the toolkit doesn't have. For instance, the version 7 signed processor will be able to work with super elements, and I don't believe that response sim does that. So it's better if you start straight from a regular solution 103 as opposed to the one response simulation.
So, but try to use that one. I'm going to edit this solution here, and I was doing case control here. I'm going to click sign. So, model effect mass, we want plot. I'm going to ask for stresses, so I'll make sure those are on, yep. We can put corner. By default should be on. Parameters, and this is where I tend to have an issue with the earlier versions of NX10, so I have trouble finding these. Perfect. So if I say this is sine, and I go to ResVinner, we're going to use the residual vector approach, so I'm going to ask for turn near ResVinner to yes. And you see over here, something we're going to click on. There we go. I think old modeling object called sign, and it remembers. Reservoir, I've got my output request. And do I always forget to do? Drag my strength. On my laptop, I think it'll be pretty quick. I should get 16 modes. Oh yeah, I had my original 10 modes, and then these visual vectors here, modes 11 through 16. And you can see the frequencies are between 72 and 141 hertz. So now, which I have, I have those eigenvectors. I'll go to toolkit. I'll do open this time on the OP file. I'll import the universal file. I have to redo this because I switched computers. We'll start defining our load cases. I'll just put one axis. What I'll do is I'll import the spectrum from a file I have on the disk. Not all. Input. So what that is it's just two columns. That's frequency versus acceleration.
You can enter that manually right there instead if you wanted to. That row
I could
below.
manually. Yeah, for example, I could add something at 40 hertz, say, to show you 5G here. You can just step in it. 25 hertz, yeah, around here. And these are in G. Solution is an inch per second squared, so I got to put a scale factor. I'm in the wrong unit system.
Not doing that as your unit will pass.
What? Exactly. It's just remarkable how the stress goes away. So now I have to go back. I clicked on output request, and I'll start by my frequency set. So I'm going to define two frequency sets. One tag or contour data, and one for plotting. So this data, and we're going to go 50 hertz. And ask for my natural frequencies and nothing more here. Okay? And the start and the end frequency. That's one. Okay. That's data. Create another one. I'll call it plot. And then just to it, so it gives me a nicer plot, yeah. Of course, you want eigenvalues. I'm going to pick FREC 3. I'm going to set frequencies to range. Between natural frequency and now I get 10 points. And I'm also going to create an additional frequency at 25 hertz where my stepwise so I can see the step in the plot. Otherwise, I might. So I got 1 is my frequency. For margins of safety. I'll pick 1, which is just at the natural frequencies. And here I can't pick groups or anything. I mean, it's all defined by the stress cases I will define later. So, just get that. Then I'm going to ask for some contour results for accelerations. And I'm going to do a universal file. Only for my net frequencies. I'm going to have relational components. I'm going to put a scale factor here. Make it interesting. And I'm going to select subreflector here for this demo. Then I'm going to have some acceleration plots. So what I'm going to do is I'm going to turn these guys off. And I'm going to set 2. I'm going to ask for data in all formats. So HTML page cell. I'm going to create scale factor. For my groups, I'm for a response nodes. I have a group of nodes over the structure. So I've got 1 load X, 3 output requests. So I can hit definition. For frequencies, I don't think it matters, but I'll toggle off, include residual flexibility factor here, so I don't think it makes any difference. We're going to keep absolute results. For default damping here, 25 to between 1 and 1,000 hertz. Output, leave it to real imaginary. I'm not going to data in the text file. I'm only going to look at it in an X, so this doesn't really matter, sort 1 or sort 2. So here's the margins of safety based on von Mises stress. We're going to create a stress case. The only component there is that feed, that horn there, so I'm going to and we'll see that handled in the random processor. So 20,000 psi, safety factor of 1 point. Call it yield. And you can have a lot of results. I'm going to put a high number here for my minimum margin, max margin of safety for print. I want to be able to see cover all the results. That's 1. I'm going to for the same elements, but for ultimate. This time, you know, some different depending on which allowable you're using, ultimate or yield. So here, I'm going to put a different allowable stress and a different safety factor. I'm going to put max for print again.
Safe because it's only based on that one material. If you have an assembly file with multiple materials, really meaningless for margin of safety the way I see it. So I just usually put 1.9 for the margin of safety to play everything, like you said earlier.
Yeah, you know, you just create more stress cases, and then you for group, you define a different material level. I mean, it doesn't store the ultimate strength and the yield strength in the MAT card. Otherwise, we can go directly out of the OP2 file. You know what I mean?
Yeah.
Okay, so I've done that. And let's click OK, and let's start this guy. You notice, right, 16 sets being processed, right? So My first resist at 70 hertz. I'm exciting up to 50 hertz, but it's not all the modes. So those serial vectors are being excited. So let's go look in our directory and look at files here. Clean because let's look at our HTML page. So our acceleration plots, and I only ask for translation, so I only have X, Y, and Z here. Right? I factor 386, so that is scale. That's a quick one. I also have plots to go to Excel, so I have this result here called acceleration graph and macros. Really, the same HTML page is actually here in the sheet, and links to each graph here, and you can see the plot rated. Same as the magnitude only, but at least I can work this data in Excel. I can do something with it. So we're going to bring this into NX. So NX has got here. New file, associated function file. So I'm going to create a new one. I want to call this sign2, and I'm going to import a universal file. Universal. And universal file is generated. Oh, I mean, it's the wrong file. Because I wasn't careful. Sign.unv, this one here. You can see in Navigator all the plots show up here. I just double click on one. I mean, you can then superimpose. I told wrong here. That's just I don't think we write the Jacques. I don't think we write the units data set to the UNV file, so it doesn't know what to write.
Yeah, that's correct.
So I think if you really fix this, you just edit it, and it's a bit of a pain. You have to do it for each one, but then you like put G's here, and it's not going to scale anything. It's just going to change the display here. Function tools, as I said, you can overlay these things. You can, click, do things like that. Windows. I mean, you can, go to log scales, really functions, and you can remember where to get the file. I think it's under response. So let's give response some credit. There's some math, all math, overall math. So what you can do is you can scale functions up and down. You can create envelopes rather, and so a bunch of responses, and you want to pass on the maximum to somebody. Well, you just the maximum envelope for all of them. So very powerful, and for the random processor as well, same thing. And I'll show you a bit more functionality you have with the random processor. All right, so in the contour data into NX. So how do we do that? Our solution, what I'm doing is I'm going to unload it. So I'm in the Post Navigator. I pick our solution and I unload. So I go back to my sim, pick the solution, go add companion result data here. Companion results. Okay, let me step back a bit. In any post, you see in the screen, in the OP2 file or in the results file or whatever, ANSYS, Abacus, whatever file, entry is always written results file, and that's what you see. The companion file, however, does not need to have geometry. It uses the same geometry as in the main solution file. So we're just going to pixel file we generated. And what was in the margins of safety? Their acceleration. Here. So now what I'm going to do is I'm going to go back to the Post Navigator and I'm going to load the solution. And now there's an extra subcase here. Sign load case 1. Okay. More than I thought there would be. My margins of safety. That doesn't look right. Shouldn't be that much stuff in there. So let's remove that. Yeah, I did something wrong. It looks like when it's done right. So I'm going to unload this. That's more like it. I must have screwed up in my effect definition, Jock. That's all I can think of. Alright, so for accelerations and von Mises stresses, so von Mises stress. My lead is here. Yeah. So if I edit my pose view, I can't convert that to anything. Extract the phase at which the maximum von Mises stress occurs, so it's a real data. You can see the safety. So what you might want to do for the margin of safety is to invert the color bar. So the low margin become red, right? So I can just go invert spectrum. Coordinate system is kind of annoying. Let's just move this to the left. Alright. And I had two for Yale, one was for Ultimate. I can just go look at the one for Ultimate. And my margins are, that's because I'm at 10 Hertz, so presumably if I go here, yeah, there's 80%. So I can see here. I also look at acceleration. Ask for now it's not going to format. So what I'll need to do is I'll use spheres or arrows. Here's my max acceleration, and it does say inch per second squared, but those are definitely G's here. So this is something that we need to handle better in the next version. I think that's done because we're using an OP2 file. This is in an X. So residual vectors. So what I can now is, if I want to run this without residual vectors, I can go in the sign processor, and I can also just frequencies and pick a range of modes. Right? I can just, that's what I could do. Of what it would be, I could just clone this solution here. I can edit this, say, sign. And then in my editor, and I remove the ResViner. I want to save it. Right. So what I'm going to do is I'm just going to point to none. All right. So that's create a, and then I just a new OP2 file. I only have 10 modes time. So here they are, modes. I'll just go get out of my processor, just go and grab that, click open. No ResVac. So I do, then I can just load the IMP file that I was using before. Here. And I'm ready to run. Okay. So what's the impact of not using residual vectors now? So we import the, I'll create a new, call it sign ResVac. I already have one, but there we go. And then just generated. And we can look at the difference, like this is before and after. Whoops. Because, oh, that's what would have made a difference. Alright. So here I set for this guy here. I put it in G's. Pick one that I haven't converted. And you can see there's a bit of a difference down here in the low frequencies here. Yeah, sorry, the bottom of this plot. Not really. You know, 1.2. So for this, there's not much difference. Maybe there's some more that have a difference. So that looks pretty similar. Okay, well, there's a bit of difference here. So that's a way, you know, easily comparing the difference between the two solutions. And with the DMAP, I can run this with the bases, and ability approach and see how that compares. Well, I won't do that now. So that's with the sign processor, and it's right now. Now, let's do this here. So, more what you've been using. Processor. Our chart of dynamic excitation. So we're moving from deterministic to non-deterministic, if you will. Random, what we call random, stationary process. So that doesn't change. It's the statistical properties don't change with time. And we'll look at what that means in a few slides. So, much the same way as for harmonic loading with the sun processor, the random processor reads a Nastran solution 103 solution, evaluates the responses subjected to base excitation, this time random. 111, except much faster and much more accurate. And one of the nice features about it, though, is that it does give the same for the sign processor. If you look at the components of the same components that Nastran does, because we're using the Nastran eigenvectors, right? You don't have to worry about different results. I'm sure you will for von Mises, because we compute things differently. But for the components themselves, all right, so that's good. As a matter of fact, speaking of comparison, here's one. So we're looking at sigma xx for a particular element, and we're saying the Nastran result with the SA toolkit result. So non-deterministic. So it means that you don't really know what the magnitude of the responses at any time. But statistically, by looking at the mean, the standard deviation, and I guess the cost, we can work with that. We can get meaningful results. There is a zero mean, a Gaussian, stationary, ergodic random process. So, and I guess that's why I've seen this question before. In the user period at Siemens, can I preload, or can I put static offset for random? And the answer is no. I mean, it assumes, all the theory assumes zero mean. If you offset the mean, then the basic theory that's used to evaluate the response is no good. So I'm not sure results are, but I certainly wouldn't do that. State means that the statistical properties are independent of time. Ergodic means that if you pick any sample, well, it represents what the ensemble of samples does. Gaussian, the distribution doesn't change as a function of operations. So if the excitation is Gaussian, so will be the response. And responses that we have are Gaussian. And they look like the probability density function for a zero mean Gaussian, so I've removed the mean from the equation, is related to the standard deviation sigma using this equation. Can I get rid of this thing here? Little recorder. Okay, looking here, we've expressed the x-axis as a multiple of stations, or this value here, which is the ratio between p and the standard deviation, or the RMS. So here's minus deviation, plus 1 standard deviation, plus 2 standard deviation, minus 2. So the probability of the value x lying between minus c times the standard deviation and plus c times the standard deviation is by getting the probability density function from sigma to plus c sigma. So let me annotate here. So the probability of being in here, I can't remember off the top of my head. I don't write it down. For two is about 60%. That's you have a confidence of being chance of having a response that's lower than that, than twice the standard deviation. For 3 standard deviations, it's 99.73%. And then you can go IF. Once evaluated, well, if you remember the transfer function we looked at before, for sine, essentially, this is a transfer function. So the response spectral density is the input power spectral density times the spectrum, which is multiple of the eigenvectors, the modal participation factor, the transfer function, and conjugate transfer function. Anyways, make it short, what it is, the variance is the integral of this response power spectral density from the upper limit to the upper limit, and those you specify in the UI. As you specify, of course, the input power spectral density. And then the root mean squared, well, is the square root of the variance. And for no integral here. That means that you're doing this in a very poor way. You'll be integrating each response. That's one of the things that we don't do in SA Toolkit. We integrate on a reduced basis, which is why we're so quick. And so we're able quickly to get you not RMS results, but you'll see the peak results as well. And mention a bit about Gaussian distribution. So von Mises stress is an example of a function that doesn't follow a Gaussian distribution because it's the square root of the sum of the squares, like Schur equations here for the 2D state of stress. And so distribution for that. I mean, to give you correct results, we have to know what it is. Okay. So here's methods. One, you can actually, if you want, you can use a Monte Carlo simulation for each result, each response. It's slow. Don't recommend do that, but anyways, you can. So what we do is we generate n samples and we sort them in ascending order. In this case, 0.73% confidence, which is for a Gaussian distribution. Then if we have some samples, and that's the 9,973rd value. That's value, and then we would plot here on the graph. Right. That's the peak value, and that's the distribution. Of course, 0. The mean is expressed by this function. Here's not 0 because the von Mises stresses are all positive. Yeah. Is expressed by this equation here, and the RMS by this one here, and then we plot 3 times the RMS with the dashed line on the right, and the peak and the actual peak and 3 times RMS, which is what people do in industry. So you'll take your strand result or your response sim result, you take the 1 sigma or the RMS result, you multiply it by 3. Well, this is by 20%. You're off because it's a Gaussian distribution. You've assumed it was. In fact, we published for the NAFAMS World Conference last June. I give the reference here, and I'll be glad to send it to you, in which we investigate error and making that assumption for antenna models similar to the one that I'm using here. And we're up to 30% error in some cases. Well, the good news, you use the approach from Nastran, you're conservative. You're not breaking anything, but you're just, you've eaten up your margin, not necessarily. Another metric, which is won't give you the same distribution, which is the Tsai-Wu failure index. So, you guys use composites?
Very case, but maybe one day.
okay, you're equipped to do it for random, because the random processor will give you peak ply stresses and your metrics, so failure indices, strength ratios, margins of safety. To our knowledge, no other software does that. It's complicated because if you look at the failure index equation for cycle, you've got some quadratic terms, you've got some order 2, some order 1 terms as well, in terms of the stress tensor. And then the stress is even more involved because you've got to solve for the roots of the second order equation by substituting the stress component A. So I'm trying to solve for that. So, and we're handling that accurately. Use Monte Carlo simulation like we did for von Mises stress to establish the distribution, and then we know that our approximation is accurate. Approximation, this is what we do for von Mises stresses. The main reference is the Segelman paper. I mean, this is the, this is in there. You probably have a copy of it. And Monte Carlo on a real-life model because it would not be performant enough. So the approach, the default approach in industry is the Segelman method. Each element, the von Mises stress is transformed into at most 5 independent stress processes, and they're identically distributed Gaussian processes of unit variance, and the random process has been studied in depth. We know how to compute values. The probability of the von Mises stress exceeding a certain value is defined by this integral here, which is a volumetric integral up to 5 dimensions. How we solve it. It's timing to evaluate. This method does evaluate it. We have a fast approximation method that, as the word as its name implies, approximates the integral and is faster. One step ahead of the Segelman method. And if you want to methods, so Monte Carlo, Segelman, and fast approximation. The first is statistical, the other two are analytical. The Monte Carlo is excellent when you have lots of samples. Segelman is good. It tends to overestimate the von Mises stress, whereas a fast approximation has got good underestimated a bit. Monte Carlo, of course, is very slow when you have lots of samples and it's accurate. Segelman is fast, and then fast approximation is 10 times faster than Segelman. In terms of we offer parallelization for the Segelman fast approximation methods. Limitations there, the fast approximation only works for high confidence levels. So if you're 90%, you should be using Segelman. Typical standard is 3 sigma, 99.73%. So in that case, you're okay to use fast approximation. So what other does our product have? Allows you to do 3 load cases in a single run. Residual flexi, residual vectors, in the same way that the SIME processor does, so I won't go into that again. You can pick them using the modal superposition. It computes relative displacements, accelerations, and velocities, optionally. It's got a hybrid integration method. And the advanced version, it's parallelized, so it's fast, it's very precise, and because of the hybrid integration scheme, does not you don't have to specify additional spectral lines or worry about having too many or too few. All handled by the integration scheme, so you can do better at night. I know, I'm just joking. All right, so else, we output the power spectral density functions, the peak values. So the peak values are onto the confidence you specify. They essentially are like 3 sigma values for Gaussian distributions. don't have to multiply your RMSs by anything. We give you the peaks. We have positive zero crossings. I'll get into that a bit later. That computes exact peak von Mises stresses and margins of safety from those von Mises stresses for the elements that you select in the methods that we just described. For composites, it computes peak failure metrics. So failure index, strength ratio, margins of safety for 2D and 3D elements, using either the PCOMP, PCOMP-G, or PCOMP-S physical property types. The bonus, we output, processor outputs results in OP2 and universal file format, so in full post-processing using NX. The question was asked by Dave, will NX85 work? And yeah, Jacques verified that it would. Again, this is using the advanced license, so it's just a way of, how can I say, also an OP2 format guarantees that NX can process the results. There is binary universal files as well as for the margins of safety data set, because the OP2 file does not have a data set for margins of safety. Number of files, well, that's used essentially, it's like an apparent frequency. So equation essentially, I won't get into the equation, but you integrate omega squared times the power spectral density as opposed to just the power spectral density, and you take the ratio. It gives you a frequency for each result, and that people use in durability analysis. So as the actual occurrence of each result.
Thing here, I guess a lot of times in the past we've taken, you look at the modal responses and say, here's the major resonance, and you use it for the number of positive crossings. But this is probably more accurate because it includes an overall effect of all the resonances. Is that right?
Exactly. Yeah, exactly. So if you've got, I mean, if you've got a single mode that's creating all your stresses or your displacement, then okay with the method you described. But if you have more than one mode that's got significant energy, then not accurate. So mine is this result, which is freely available to you. So the input looks a lot for the MF, for the modal effective mass approach, looks exactly, as a matter of fact, like the one for the sign processor, except that if you're going to ask for displacements, accelerations, velocities in binary format, you need param OUG chord mobile. And the rest is exactly the same. So look at the user interface. It's split up rather neat, I think, in terms of the your workflow. So you define your base PSD, the power spectral density. Pick the frequencies that you want to excite. Define your damping, analysis parameters such as confidence level. Then, much in the same way as in the sign processor, you define your stress cases. Right? So with these cases, you will get the von Mises stresses and safety. If you just ask for stress output in the request, which is the next box, you will not get the von Mises stresses. You need to create stress cases. The base acceleration dialog allows you to create subcases. Again, you can read in it. You can define your curve using a set of points, frequency and power spectral density. You can scale the power spectral density such that you can express it in G's. As a function of G's, which is typical industry. Here is that you don't specify your output requests on this dialog. All the output requests you define are applicable to all the subcases, and they're defined in a subsequent dialog. Frequencies, you can all your modes are a subset of modes, whether by frequency or mode ID, for your modal superposition. You would residual flexibility effects using checking on this toggle when you're using the DMAP approach. Absolute and relative, we talked about that before. And this is what you want to define your upper, at the bottom of the dialog here, your lower and your upper bounds for integration. You can function from 20 to 2,000 hertz, say. But you can only integrate, say, between 100 and and 200 hertz. You don't need to find your function. Your modal damping is defined exactly as a sine processor. There's no difference. And is expressed as an amplification factor Q.
You can run all three axes at one time, but if you have different modal dampening for the three axes, then you really have to run them individually, X, then Y, then Z.
That's correct. The analysis to define your confidence level. So since we calculate the peak values, the results are non-Gaussian, we don't allow you to do 2 or 3 sigma. You find a confidence. The confidence you can type in as a percentage, or you can type in a peak to RMS ratio, and we will calculate the confidence level on that. And that's what we're going to use in our evaluation of peak results. And goal confidence level again is the equivalence of 3 Gaussian standard deviations is 99.73%. So, sigma or RMS results. You can if you want. Right? But you don't need to anymore. Integration scheme, I mentioned before, we have advanced integrators such that you don't need to specify the frequency, the frequencies, or number of spectral lines. Use double precision arithmetic, and default scheme of selects the most precise integration algorithm, either analytical or numerical. Analytical is exact. Numerical integration uses an adaptive and robust algorithm. The advanced option is the same, a hybrid, except there is no, it's completely numerical, there's no analytical portions. Define stress cases. In days before last approximation, we calculate approximate von Mises stresses, and information is that little plus sign there, the bottom of the equation there. It's worst, and we calculate worst case von Mises stresses, and we'd give you the option to calculate accurate von Mises stresses when that was high. You don't read that anymore, but it's there for legacy reasons. If you use the approximation, you don't really need to worry about that at all. So when you define a case, whoops. Okay, sorry. I'm going too fast. Yeah. There's Sigelman fast or fast approximation on the dialog there. Again, Sigelman only if you have low probabilities, like 1 sigma. Monte Carlo, you can use that. You have to enter that toggle in the definition file by hand. Best case dialog. Similar sign processor. You select the elements that you want to process. You define a allowable strength and safety factor. The von solution, if you're using fast approximation, use exact only. If you're using a Sigelman, you can use calculate the worst case margin, Mises stress, and then when the stress is below this margin of safety cutoff, we'll turn on the Sigelman solution. The stresses and the margins, the margin below this cutoff here will be printed. If you want all the stresses, put a big value here. And margin fee request then works on the cases you've defined. The stress must be available in the OP2 file. As a sign processor, the corner requests are supported in the nodal. So for an element, you can look at the centroid or nodal results. Here it's your choice. And the corresponding margins of safety are sent to a file, Excel file, or a binary file. Exception, displacements and velocities. Again, you only need the displacement result in the SALT 103.
If you went to the last slide, and let me ask a question.
Yeah.
a corner no versus corner yes, the difference? Would you met?
What I'm saying is that's available. It's not available for the sign processor. Corner means it looks at the nodal results.
Stresses, I'd have to say yes.
Yeah.
Okay, but I also get, so that's more results. In other words, if I say yes, I also get my elemental centroid and all, right?
It looks at the worst of all. Yeah. So it's one result per element, which looks at, and that result is the worst case result for for the centroid and the corner results, which are nodal. Yeah. An option for scale factor here for the acceleration results, so you can have them in G's. That does not apply much. It does not apply to the binary results that go into NX. Those are always inconsistent. So I just mentioned that. And then there's a composite failure metric selector. So for failure indices, strength ratios, and margins of safety. Again, the stress eigenvectors must be in the OP2 file. Strain as your failure theory. The strain eigenvectors have to be there. The strains are output using the stress strain output request, and directly in the OP2 file. They're in the POM cards, or in the there's another card for that. Jacques will know, but I got not Matt said, but anyways, they're in the OP file. In terms of plotting, the plotting options you have don't affect at all the results. They affect how the plot looks. And again, you select the natural frequencies, additional frequencies using the FREC1, FREC2, FREC3 paradigm. Nodal results or corner results. Before they were read by SA Toolkit. In the old days, the corner results were evaluated, but then they were written as an elemental result. Now, throughout as elemental nodal results, whereas the corner results are only evaluated and they're not mixed with the rest. So the centroids before and after V6 are different. So much better mix. As a processor, we output an HTML page with a directory listing. You're going to Excel as well. For the sign, we recommend that when you open your sum file and make sure that your input power spectral density is correct. You should assign as well. And your input, you're just plot it like if it was a response, and make sure exactly the same as what you input. So if any unit errors, you'll notice them there. Available from the binary, so contours of accelerations, contours of stresses. When you see a root actually appearing in NX, that's not true. Those are peak results. It's just that we're using the root mean squared data block, so we don't have a choice. They are confidence you define. And read the functions, the power spectral density results as functions by point time. Instead of to a universal file, you point it to the OP2 file. The results are in the OP2 file directly. So I ran a demo to show you that. So the idea is I'll generate the solution again. We'll generate USOL 103 solution. And my output. That's stresses and displacements. You must remember that plot. Stress fault, but by default only corner here. And then we don't really need, oh yeah, we need param UG core global, right? Because I'm going to ask for, accelerations. Oh. Okay. Sure there. Okay. I just got to drive my constraint. My solution. I solve it. Basically the design processor except for the extra param. In this case, I'm specifying any residual vectors. I could if I wanted to. Right there. So I'm going to open this OP2 file, like Y failure indices, my stresses, mode shapes, CC force. So I'm going to use the random processor, finding a power spectral density, and fine, I'm just going to read in a text file. So my directory the sort type. So random is, and you want to see what it looks like. All it is, it's space limited, 2 columns, frequency and PSD. And because I have PSD and G squared per hertz, well, I got to put a scale factor in here. And my model is in second squared, so I put 386.1. And as they enter these by hertz, so I did 3,000 hertz, something else smaller, say. Curve looks like. Another one, say another subcase. Excite me. 6.1. I'll import this. Can't just copy from one to the other. I'm going to use the depth for my modes, except I'm just going to go from to 100. My damping, cube 25. I'm going to as a hybrid by default. My confidence is going to be 99.73%, 3 sigma. Yeah. I'm going to use approximation to get my stresses. I'm going to create my feed. Just one. Cut off here. Okay. So margins of safety, of course. I'm putting them in the binary file. Then I'm going to define failure metrics. I'm going to put them to the binary file. I'm not going to use there are none for 2D fly elements. My safety factor, put a factor of 2. Do this for the subselector only. Animation output. Excel, I'm going to put it in the binary file for my for what? For everything. And then here's some Excel for my response nodes. Nope. Yep, we're done. So what can we, well, first let's look at some of the metadata. I've got HTML, the sign processor. Except I picked the sign results. The random result. Huh. Okay. So I've got two result cases. You can see that in the navigator here. File. And look at them there. I've done that before, so I won't. I'm going to just bring the Z's into an X. What you do now is just go, see Nastran OP2, sort 2 results here. Actually. The results of this. The acceleration units, inch per second squared, squared per hertz. Let's change that if you just edit it. Change that to custom G. So we put in the OP2 file that are always inconsistent units, and you can modify them later. You can see RMS of this result here in NX. HTML page, it was there. See the RMS right here.
So they're very low, aren't they? I don't believe you put the acceleration of gravity in your kickoff request, did you?
Gravity. I mean G's?
Your sector. If watch your inline, is that your inline there? Basic acceleration node.
This is in the x-axis, so it's pretty high.
You just use 0.03, did you?
Yeah, that's 4G's RMS there. Yeah. This is
okay.
nice. That's a bit less. And the Z's got virtually nothing. So you have RMS values here, and you have them in the Excel file. To get them into NX, if you click information on the plot, you won't see anything. So you just go export. If you export these as is, and I'm going to say Honeywell. This is an FYI, a UAFU called Honeywell. Didn't pick anything. That was brilliant. Huh. Put that in the folder. Let's do it again. If I pick these here, for I must have the wrong folder. antenna. Okay. Right. Then once in AFU, for some reason, I can click it, go information, and you'll see the options appear. Okay, so you can't do the plots in NX. It's just that you have to convert the plots. You have to take them from the OP2 file and generate records of them for some. All right, now bring 2 results in NX is easier than because you don't have a companion set. As a matter of fact, what I do is I just can use solution random results. Leave it at 101 and just go pick this here and just go specify, and I'm just going to pick the file is generated here. Cases. The von Mises stresses here. Just turn off deformation doesn't really mean much. My von Mises stresses. For each plot. Second slide. So this is really amazing that you can get this metric solution. Failure indices is the interlaminar inter-strength ratio, the ply strength ratio, which is how much, it's also a reserve factor, so you want this to be bigger than 1. And then, so the RMS acceleration. In X, Y, Z, and crossings as well, right? So it varies between, well, the base is more like 5 cycles, goes all the way to 61. So it gives you more of that. 60. That was my now. And you've run big models and you've generated these statistics, so it's really fast. Why is it so quick? Why is the random processor so quick? We have 10 minutes left or so. It's got an efficient OP2 reader. It's got a fast approximation for von Mises stresses. It's parallelized. It uses a very format integration scheme. You put all, and of course, you know, you get something that's really exceptionally fast. It's accurate. It's accurate because you can account for modal truncation. Because you have to worry about having enough or too many frequencies. Because failure metrics and your peak von Mises stresses are accurately computed, even though they're not Gaussian distributions, and they've been validated using the Monte Carlo method. So I wanted to show you today, as I mentioned, examples that come with the product as part of the help package. I will do them, or we will redo them, and we will send them to you so you can practice with them. But in the meantime, I hope you can practice. If you have any support questions, send them to support@myhtt.com, preferably. Email or me. Jacques. Nice features in V7. And I can tell you that we're not supposed to talk about the future, but I think the sign processor is going to be it's going to support, for example, results. It's going to be a better product.
Right? file and create that.
That we're looking at. So
Perhaps.
with Linux OpenScript that does it, we're not at liberty to distribute it right now, unfortunately.
Okay.
So hopefully in V7 there's a smart, just a one button way of getting the group set.
Well, again, when can you expect the I'd like to talk to Rachel, and so everybody can start using get loaded with it.
For us, it's a matter of, as Mike said, it's a matter of a day for us to generate the licenses. So,
It really is
person again?
modify license to accommodate our to accommodate everybody. So more than two temporarily, I think.
Okay, it would take us a day to turn that around. I guess I wanted you guys to make a request for it. So just fire an email telling us what you want, and we'll turn it around.
How many we need? Is there a limitation on how many you give us? Typically, or how long will they last? Also,
That's a good question. After this here, how long do you guys think you need to be there?
I think yours is good. No, I don't know.
You guys ordered that, right?
Talk it over with Mike. Hey, anything I need to do to make a request or whatever we need to do. But with this better.
Come up with, I don't know, a couple weeks, something like that, and hopefully that's okay for you, and then we'll give you the, and we'll turn that around.
Thank you. Really good. And any more questions, or are we good?
Yeah. Guys, I did have a question. I noticed, earlier on you mentioned that the approximation can sometimes be optimistic. Have you ever had any test cases where you've seen that?
It's up to about 2 or 3% optimism. I mean, right? It varies with the stress.
Yeah.
So what
if you notice it varies in certain cases, like if certain types of models tend to make it more optimistic, or if you've done anything like that.
Okay, I'll ask Jacques about that. I have to leave, so.
Okay.
So you run the analysis, your stresses, and you apply your factor of safety, and you're within 2%. You better do it the slow way. Is that way?
Well, with fast approximation, you don't need that. So if you toggle on exact, it's not even going to calculate the worst case von Mises. It's just going to use the fast approximation for all your von Mises stresses.
But if you're 2% optimistic potentially,
Or
are you saying go to the other method for the you're within %? Oh, darn afraid.
Oh, that's a good point. Sorry, I hadn't caught that. Then I guess, yeah, you could consider going to Sigelman, or at least those elements. I could group
Or
with
could
those
you
elements.
Or you just tack on 2%?
But this might be that you're dead on.
Yeah.
So if it's redesign, then before you go to redesign, you'd probably do the second one.
Yeah.
If you've noticed anything like, say like larger models with lots of metallic structures tend to have RB than say a composite structure, may be more optimistic or something like that.
We'd be able to deduce at that high level of say, if you want, it's more what your stress tensor looks like. So I'll see what Jacques has to say.
be able to, you want to email everybody this presentation, or you want to email me to distribute to everybody?
I prefer emailing you if possible.
Okay, just me, and I'll everybody that signed up, and we'll put it on the our shared drive also. And you also have a recording. If you would email that to me, and we'll deal with it.